Okay, hello everybody, this is linear algebra and seminar 15, and now we start with the quiz. And first of all, we will discuss these tasks. We will try to give the correct answers for this quiz and for these questions, and prove, so justify our answers. Right? Task number 1. So the first question is, if u in W and the same vector u is in W perp, then u is a zero vector. Is it true or false? Okay, true or false? Is it true? True, right. Correct. It is true. And now let's prove this. Okay. So by definition, W perp, what is the definition of W perp? So given a subspace W in Rn, we can define W perp as the set of vectors x from Rn such that the dot product of x times y equals 0 for any vector y from W. So this is the definition of W perp. And on the lecture we have proved several properties concerned with U perp, so orthogonal complement. And one of the most important properties was that Rn is equal to the direct sum. So the sum of these two subspaces. So W perp is a subspace, is also the subspace of Rn, and this sum is a direct sum. Okay, this means that the intersection of these two subspaces consists of just a zero vector. And so if we have the vector u, which lies in W, and at the same time u is in W perp, then u is a zero vector. This is correct. Okay, I hope it's clear. Okay, task number 2. Okay, if two vectors u and w are u and v are orthogonal, so u is orthogonal to v, this is the same as by definition. This means that the dot product of these two vectors is 0. Is it true that this equality takes place? No. Okay, no. So it is false. So the answer is false. And now let's prove this. Okay. So what is the correct equality for two perpendicular, mutually perpendicular vectors? If two vectors are orthogonal, then what is true?
The squares.
Right. Pythagorean theorem. Right. Pythagorean theorem. Pythagorean. Just a moment. I will check them. So, or maybe, okay, Pythagorean theorem tells that u plus w squared equals the norm of u squared plus the norm of v squared. Okay, this is Pythagorean theorem, but this is false. But this equality looks like a triangle inequality, right? By triangle inequality, it should be this should be less than or equal to the sum of the norms of two vectors, like right, if we have the vector u and the vector v, then u plus v is this vector, and the norm of this vector u plus v, the vector u plus v should be less than or equal to the sum of the norms of the given vectors. So this is triangle inequality. Okay, and equality holds if and only if u and v are parallel, are proportional vectors. Okay, so number 2 is false. Next, question number 3. Every orthogonal matrix is orthogonally diagonalizable. Is it true or false? Orthogonal matrix is orthogonally diagonalizable. Okay, let's recall the theory concerned with orthogonal diagonalization of matrices. Okay, matrices which are orthogonal diagonalizable. So a matrix A is diagonalizable. A matrix A is diagonalizable if and only if there exists some matrix P such that P inverse times A times P is equal to a diagonal matrix. So this is notation of the matrix of the form lambda 1, lambda 2, and so on. These are entries on the main diagonal, and all the entries that are off the main diagonal, so other entries should be equal to 0. So this is a diagonal matrix. Okay. But what is orthogonal diagonalization? So sometimes we are interested in orthogonal diagonalization because, so in this case, we require that the matrix P be orthogonal. If P, so if P is orthogonal, then A is orthogonally diagonalizable. So this means that if we change the basis, we come from the orthogonal basis, we move to the orthogonal basis. So this is the distance preserving linear operator, and so it is very interesting for us. Right? Orthogonally, P is orthogonal. And do you remember which matrices are orthogonally diagonalizable? Do you know? There was a theorem. Symmetric matrices, right. A should be symmetric. So A is orthogonally diagonalizable if and only if A is symmetric. A is symmetric. But not orthogonal. Okay, so orthogonal matrix is not orthogonally diagonalizable. Only symmetric matrices are orthogonally diagonalizable. So, well, let's go to question number 4. If A is a real symmetric matrix, then this product, A times A transpose and A transpose times A, are orthogonally diagonalizable. Kathy, do you know? Is it true? What about number 4? What shall we do to check this, to answer the question?
We should check if
This product is a symmetric matrix or not. Right. Let's check whether A times A transpose is a symmetric matrix. How can we do this? What is the characteristic property of a symmetric matrix?
B transpose is
Right. A transpose, or B, maybe B is symmetric. Maybe I will use this space. B is symmetric if and only if B transpose is equal to B. So let's find that, so let's transpose this matrix. Let's find the transpose of this matrix. What is A times A transpose and transpose? So which properties can we use? Okay, so if we take the transpose to the product, the transpose of the product is the product of the transposes to these matrices written in the inverse order, right? Reverse order. So it is A transpose transpose times A transpose. What is A transpose transpose? We make a reflection in the main diagonal, and once again we make the same reflection, and so we come to the same matrix, right? So it is equal to A times A transpose. Right. So we can see that the transpose of this matrix is the same matrix. So it is symmetric.
why is it specified that it's a real square matrix?
Real. So because next time, so today we will discuss unitarily diagonalizable matrices. And so we will use, if we have complex matrices, then they are unitarily diagonalizable if they are Hermitian matrices. And so we have so the operation. Okay, but if it is real, then so if we have complex matrices, then we should take the transposition and the conjugation to the matrix, right? So for complex matrices, we consider the operation the conjugate transpose. It is called conjugate transpose. So we should take the conjugate and we should take the transposition. And we will discuss these matrices. But now these matrices are real, and let them be real. Okay. Okay, so it is symmetric. And it is orthogonally diagonalizable. So the answer is true. So it is true. Okay, and the last question, number 5. The inner product of two vectors cannot be a negative real number. Is it true? The inner product of two, false, of course. So the inner product is a generalization of the dot product. So we may, maybe it is more convenient to give the example of two real vectors whose dot product is a negative number. For example, let it be u, let it be maybe 1, 2, and 3, and v will be minus 2, minus 1, and 0. Right? Then that in the product of these two vectors, it is denoted using these triangle brackets, right? So this is the notation for the inner product. So since we have two real vectors, then we may use the particular case. So the particular case of the inner product is the dot product, and it is equal to 1 times negative 2 is minus 2. So next, 2 times negative 1 is minus 2, plus 3 times 0, and it is equal minus 4, it is negative. So it is false. Well, we have discussed all the theoretical questions, and now the last question was the small problem, and now we will discuss it.
Yes, Rohan, we can hear you. Hello.
Question. Which one? Ask the question if you have. Вопрос. You may use the chat to answer the to ask the question. Rohan. Well.
Yeah, is the third question true or false? From the next question, I'll use the chat. Is the third question true or false?
Which one? Which question?
Is the third question.
Third question. The third question is false. False. It is false. Because only symmetric matrices are orthogonally diagonalizable, but not orthogonal matrices.
Oh, okay, I understand. Okay.
Well, thank you. Okay. Okay, task number 2. The task is, so find U perp if U is a span of the following vectors: -1, 2, 3, and 2, 1, -1. So in R3. Let's find U perp. So by definition, U perp is the set of all vectors that are orthogonal to the vectors from U. But we have proved on the lecture that it is sufficient to check the orthogonality of any vectors of U perp with spanning vectors. Right? So by this theorem, X is in U perp if and only if. So we will use the dot product because this is this task is from the preceding seminar, and we deal with dot product, real dot product, not inner product, right? So X is in U perp if and only if. So let it be, I will introduce the coordinates, let it be x1, x2, and x3. And then X is in U perp if and only if the dot product of these two vectors, X with the first vector, let's call it V1, and let it be V2. So the dot product of X with V1 is 0, and the dot product of X with V2 is also 0. And if we solve this problem, we will get the answer. Solve this linear system, right? Let's find the dot product of this given vector X and the first vector V1. What is the dot product? It is equal to minus 1 times x1, so minus x1 plus 2x2 plus 3x3 equals 0. And the next equation will be 2x1 plus x2 minus x3 equals 0. Now our goal is to solve this homogeneous linear system and find the basis in the solution space. And the basis will be the spanning vectors for U perp. Okay, let's solve it using Gaussian elimination method. So 2, 1, minus 1. So let it be the leading one, and I will change sign of this, alternate the sign. 1 minus 2 minus 3, 2, 1 minus 1. This is a leading one. I will multiply the first row by -2 and add to the second row, and this will bring me to the position 1 -2 -3, and then 0 5. It is 3, so it will be 5. Next, I will divide this row by 5. One. And this is the next leading one. So I will multiply the last row by 2 and add to the first row. And I will get the following. 0, 1, 1. So 1. Next, 2 times, so 1 times 2 is 0. So, right, and add here. So next it will be -1. So we end up with this matrix. And now we are ready to find the solution to this homogeneous system. To do this, I will move to the corresponding linear system. So x1 minus x3 equals 0. And then x2 plus x3 equals 0. So x3 is a free variable, and x1 and x2 are 2 leading variables. And next we should solve for x1 and x2 in terms of x3. And we will get the solution space. So x1, x2, and x3. Okay, I will regard x3 as the variable t. I will assign t to x3, and then x2 is equal to minus t, and x1 is equal to t. So t is any real value. And so all the vectors can be represented in the form t times the vector 1, minus 1, 1. And so we can see that U perp is spanned by this vector. Okay, so this is the answer. This is the span of this vector. Okay. So that's all with the quiz, and now we will move on to our seminar. Maybe I will clean the blackboard, right? So we will continue our seminar. So it is called complex matrices. It will be devoted to complex matrices. So up to now we have considered vector space Rn. So with operations, so we have vectors in Rn, so this is a vector space, and for the vectors in Rn, the vector space axioms are satisfied. But if we consider the vectors over the complex space Cn, so vectors, we can consider vectors in Cn, in the complex space. The coordinates of these vectors are allowed to be complex numbers, right? And then we may define the sum of vectors and multiplication of vectors by scalars in the same way as before, and it was done for the real vectors. And so all the vector space axioms are satisfied for the vectors in Cn, and we may speak of the so we may consider generalization of maybe matrix multiplication. So we may consider matrices, of course, over C, and consider matrix operation with these matrices. And today we will discuss generalizations of this these notions. Okay, so first of all, we start with the inner product. So inner product of two vectors v and u in Cn. So it is denoted by these triangular brackets. So let it be V, and it is U. And it is introduced as the, so in components, it is equal to the product of V1. So if V is the vector with coordinates V1, V2, and so on, Vn, and U has coordinates U1, U2, and so on, Un, then the inner product is equal to V1 times U1 conjugate plus V2 times U2 conjugate plus and so on plus Vn times Un conjugate. And now we will use this definition to solve task number 1. So let it be, maybe let it be here. So task number 1, given two vectors, not two vectors, so given a vector, compute the norm of the complex vector. Compute the norm of the complex vector. So we have the vector x, which is equal to 1 minus I, negative 2, and I. What is the norm of the complex vector? So by definition, the norm of this vector is defined as the square root of the inner product of the vector x with itself, as in real case.
Can I find out?
Okay, Ah, right, you're right. Welcome. Okay, and the norm can be cannot be complex. It should be real.
How do I denote the conjugate?
The conjugate maybe in this way, right? So because we need the bar and we need the vector, denote the vector and the bar. So this is the problem. Right. This is the conjugate, right?
No.
The inner product, right? Correct.
Plus.
So minus I think, minus I, not plus. This is plus and this will be minus, right? So I times, one is correct, I times negative 1.
Negative I.
Negative I, in brackets. Correct. And now compute.
So this is minus plus 1, right?
Plus 1, right, because I squared is negative 1, and then we multiply by negative 1, and it is plus 1. So all these terms must be positive or non-negative. So it is guaranteed by the theory. So I will, right, correct. Oh, 2 root 2, maybe. Thank you. Thank you. So theory guarantees that this must be non-negative. And there is the statement, or maybe theorem, the part of the theorem, if x is not a zero vector, then if we multiply x with itself, then this will be the real positive number. Real positive number. It comes from the fact if we multiply, so x times x, it is x1, so let x1 be the first coordinate of the vector x. Then this product x1 with the conjugate of x1 is the norm of x1 squared, right? So in terms of, so if we represent, so plus dot dot dot, so because if x1 is a plus bi, then x1 conjugate is a minus bi, and this product is equal to a squared plus b squared, right? So positive real number, right? And so each term is a positive real number, and then, or non-negative real number, maybe negative, of course. Well, right, it's this. Now let's move to task number 2, maybe. Task number 2. In each case, determine whether the two vectors are orthogonal. So whether two vectors are orthogonal. I will call it x1. It's 2a. It is 4 minus 3i. And 2 plus I. Sorry, it's not this. 4, next minus 3i, and next 2 plus I. This is the first vector, and the second vector is I, 2 minus 4i. Okay, and we want to check whether these two vectors are orthogonal or not. How can we do this? So we will use the definition of the inner product. And two vectors are orthogonal if and only if their inner product is 0. Let's check this. So let's find the inner product of these two vectors. 4 should be multiplied by e bar, the conjugate of I. The conjugate of I is negative I, plus, so negative 3i multiplied by the conjugate to 2. It is 2, because this is a real number, plus 2 plus I times the conjugate of the last coordinate. It is 2 plus 4i. Then, expanding this, we will get the following. Minus 4i, minus 6i. Next, plus 4, we multiply 2 by 2. Next, 2 times 4i, so plus 8i, plus 2i, and plus 4i squared. Let's simplify this. So this is minus 10i. Next, plus 4, plus, and this is 10i. And what is 4i squared? So minus 4. Okay, and next we can see that this is 0. So since this is 0, then these two vectors are orthogonal. This proves that x1 is orthogonal to x2. It can be denoted in this way. I will use vectors because, in order to not confuse with the complex conjugation.
Does the order matter?
The order, okay. So if we change the order of these two vectors, we will change, okay, so the order matters, of course. So the property is, so if we change the order, we will get not the inner product of x2 with x1, but we should put the bar. So the conjugate to this product, the conjugate to this inner product. Well, thank you for the question. So these two vectors are orthogonal, and next.
Can they hear me speaking? I don't think so.
Sorry?
They cannot hear me speaking. Hello.
Maybe, so I don't know how to do this.
Они слушают меня.
Они не слышат, когда он говорит, да, не слышат, видимо.
Нет, не слышат, потому что нет микрофона.
Да. Okay, so the questions, it's, maybe I should repeat the questions and then answer them, right, because they can't hear the question. Well, okay. So do we need to solve 2b? So this is the same problem. So two other vectors, and the task is to check whether they are orthogonal or not. Maybe it's easy. What is your opinion? Okay, so Rohan is here. So can you write in the chat? So do we need to discuss 2b? So the same problem for two other vectors.
No, ma'am, I think it's fine.
Okay, Let's move on to task number 3. Task number 3 is, in each case, determine whether the given matrix is Hermitian or unitary. So Hermitian and so Hermitian, this is R, or unitary matrices. What are they? So what does it mean? So let's recall the definition of these two objects, Hermitian matrices or unitary matrices. So Hermitian matrix is a generalization of the transposition, transpose, right? So in real case, we have, if we have A, we can consider A transpose. Okay, A transpose. And if A equals A transpose, then the matrix is symmetric. Okay, in complex case, in the case of complex numbers, for complex, okay, over, let it be over C. Okay, we may consider, so given the matrix A, given a matrix A, we can consider A transpose, but we will not be interested in symmetric matrices. These matrices are not interesting for complex case. So we will consider A transpose, and then, so we should transpose A and then take the conjugate of A. We can construct this matrix. And then if A equals A bar T, so this is denoted AH. So the conjugate transpose, AH means conjugate transpose. And if A equals A conjugate transpose, or if A is equal to AH, then A is called Hermitian matrix. Hermitian matrix. Okay, I'd like to maybe recall an example. Let's consider an example, how to construct AH. How to construct AH. Given a matrix, maybe let it be 1 minus I, 2I, 3 plus 5I, and 4. I want to construct A conjugate transpose. Okay, we should make a reflection in the main diagonal, and we should at the same time we should take we should consider conjugation to each entry. So for example, this entry 1 minus I, so it will not change place, it will be at the same position in the new matrix, but it should be changed to the conjugate of this entry. So it will be 1 plus I. Right? Next, 2I will go to this position because it should be the reflection in the main diagonal. So we should make a reflection. And we should take the conjugate. So it will be minus 2I. Next, 3 plus 5I goes here, and it will become 3 minus 5I. And the last 4 is unchanged. Okay, this is an example. Okay, this is about Hermitian matrices. And now let's discuss unitary matrices. The unitary matrix is a generalization of which notion? Do you know? Unitary matrices is the complex analog of orthogonal matrix. Orthogonal matrix in the real case and unitary matrix in the complex case. Okay. So in maybe I will use, let it be here. I need space. Okay. So unitary matrix. Let's compare this notion with the, so unitary, let it be orthogonal matrix, unitary. In the real space in Rn, so over R, we have the notion of orthogonal matrix. P is orthogonal if and only if P inverse equals P transpose. And we have so the other definitions of the orthogonal matrix, they are equivalent. So by equivalent definition, so this is definition number 1, by an equivalent definition, P is orthogonal if the rows of P are orthonormal or the columns of P are orthonormal. So this means that if we consider the matrix, if we consider the columns, for example, of our matrix P as vectors, then this should be the orthonormal set in Rn, right? So the length or the norm of each column should be equal to 1, and the dot product of two different arbitrary columns should be equal to 0. So this means that the columns of P are orthogonal, are orthonormal, right? Orthonormal. So the norms should be equal to 0. Okay.
Equal to 1, right?
Huh?
Equal to 1.
Equal to 1, right? Equal.
You said 0.
Oh, it's 1. Sorry. Okay. Equal to 1. Of course, yes. And unitary matrices. Okay. So over.
So it was the definition of orthonormal.
So this is for orthonormal, right? Or orthogonal matrices. But what are unitary matrices? Unitary matrices. Okay, for unitary matrices, we need, so the first condition will be changed to replaced by P inverse is equal to P conjugate transpose. Or the rows of P, so they are usually denoted using the letter U, not P but U, right? The second condition, the rows of U are orthonormal. Orthonormal in the sense of the inner product of two complex vectors, right? The inner product of any two columns or rows of U should be equal to 0. And the norms of the rows or columns should be equal to 1. So this is a unitary matrix. And now let's try to solve task number 3. We will try to check whether the matrix, the given matrix, is Hermitian or unitary. Okay. Welcome. So this is the task. 3A.
So I'll check for. Do we denote A transpose conjugate by A?
AH, right? Of course, yes. Let's find AH. Okay, this is correct. And now let's compare. Is it equal to A? So AH is found. Is it equal to A or not?
No.
No, of course. So the conclusion is that this matrix is not Hermitian. It is not Hermitian.
Now we should check for.
Unitary matrix.
Okay, so for unitary.
So it's, I think it's more convenient to check whether, for example, two columns are orthogonal, are orthonormal vectors. It's more easy. So we should consider two vectors, one I and minus I.
So I'll denote the vectors by.
Okay, let it be V and V1 and V2 maybe.
Okay.
You or it doesn't matter.
Okay. So
I think it's better to find the norm of this vector.
oh yes.
Find the norm. Start with the norm.
Is equal to 1 times I. Product 1 minus I.
Right.
Which is equal to 1 plus. Oh,
So it is 2.
so V1 is not.
Unit vector. It is not unit vector, right?
It's a square, right?
Right. It is square. U1 squared.
V1
Is not a unit vector. Right.
Therefore,
It is not unitary. So this matrix is neither Hermitian nor unitary. Not unitary. Thank you. Thank you.
Copy.
Okay, all right. Take it. Next. Okay, let's discuss 3b. And so this is the some. Here is some hint which can be used to simplify our computations. So the hint is that the unitary entries on the main diagonal of a unitary matrix should be real. Real. So, but here we have the complex, so the imaginary entry, and so this shows that this matrix can't be unitary. It can't be Hermitian, right? Can't be Hermitian. So all Hermitian matrices have the entries on the main diagonal that are real numbers. Okay, B. Our next matrix is 1 over root 13 times 2, 3i, and 2. So we have two real entries on the main diagonal. So let's check for, let it be A, for being unitary. AH is equal to 1 over root 13. And we should consider that, so we should make a reflection in the main diagonal. And after this, we should change all the entries to the, replace all the entries by their conjugate. So the resultant matrix will be minus 3i, and 2. Okay. So it is not the same as A. So A is not Hermitian. A is not Hermitian. Next, let's check for unitary, for being unitary. We will consider columns of this matrix. The first column, let it be U1. It is 1 over 13 times 2, 3i. And the second column will be 1 over root 13 times 3i and 2. Let's find the norm of U1. So squared, let it be squared. Then it is equal to 4 over 13 plus, this will be 3i over root 13 times minus 3i over root 13. Because the second coordinate is complex, then is imaginary, then it will be this. So we have 4 over 13 plus 9 over 13, it is 1. So the norm is equal to 1, so U1 is a unit vector. Okay, the same is true for the norm of U2. I think you can, so I want to leave it for the listeners, so it is not difficult to find the norm of this vector and prove that the norm of this vector is also 1. So now let's find the inner product of these two vectors. This is not a conjugate, these are vectors. Okay, let's find the inner product. So these two constants can be multiplied separately. So 1 over 13 times, and then 2 times 3i conjugate. So 2 times minus 3i. 3i conjugate plus 3i times 2 conjugate is 2, because 2 is a real number. So we can see that this value is 0. This is 0. Okay. Now, is it true that the columns of the matrix A form the orthonormal set of vectors? So the norms of both vectors is 1, and they are orthogonal with respect to the inner product.
Yes.
Yeah, so this is the unitary matrix. A is unitary. A is unitary. Mm-hmm. Okay, next. So it's B. Okay, now let's discuss C. The last matrix A is 1, I, minus I, and 2. So I claim that this matrix is Hermitian. Because AH is equal to, so this matrix has real values on the main diagonal. This is good for being Hermitian. And then if we transpose and take the conjugate, we will get minus I and I, the same matrix A. It is Hermitian, and it is not unitary. Not unitary, because, for example, the norm of the first column squared is equal to 1 plus 1. It is 2 and not 1. And so it is not unitary. Well, now task number 4. If Z is any complex n by n matrix, show that Z plus ZH is Hermitian. Now let's show that Z plus ZH is Hermitian. How to show this? So we should consider Z plus ZH and H and use the properties of this operation. So the properties are very similar to the properties of transposition. So if we take the conjugate transpose of the sum, it is equal to the conjugate transpose of each matrix. This is the first, the linearity, so the linearity of this operation. And then ZHH is equal to Z. So it is equal to ZH plus Z. So these properties can easily be proved. But we can see that the the obtained matrix is the same as the original one. So it is equal to the original matrix. So we are done. We have proved that Z plus ZH is a Hermitian matrix. And at last, we will discuss task number 6A, how to unitarily diagonalize matrices. So this is the generalization of orthogonal diagonalization. So in real case, we have orthogonal diagonalization. We have discussed orthogonal diagonalization of matrices. And we have proved that if the matrix is symmetric, so a matrix can be orthogonally diagonalized if and only if it is symmetric. But in complex case, we have proved the theorem that states that if the matrix is Hermitian, then it can be orthogonally diagonalizable. But not only Hermitian, unitarily diagonalizable, but not only Hermitian matrices can be unitarily diagonalizable. Okay, now 6a. We have a matrix which is a Hermitian matrix. We are given a Hermitian matrix. And our goal is to find the matrix U, which is unitary, so to find a unitary matrix such that UH AU is equal to a diagonal matrix. Let's call it D. D is a diagonal matrix. So to solve this problem, we should proceed as before, as in real case. So we should start with the characteristic polynomial of A. It is the determinant of the following matrix: 1 minus lambda I minus I, 1 minus lambda. So we find the determinant. It is equal to lambda squared minus 2 lambda plus 1. And then it will be plus I squared. It can be factorized as lambda times lambda minus 2. So there are two roots of this characteristic polynomial. Lambda 1 equals 0. We will start with the 0 root. And then we should solve the following matrix equation. Times x1, x2 equals a 0 vector. So now we have found the eigenvalues. The eigenvalues are 0 and 2. They are roots of characteristic polynomial. And now we are trying to find the eigenvectors by solving this equation, this vector equation, matrix equation. Okay, we will solve it using Gaussian elimination method. 1i minus I1. This is a leading one. We will multiply it by I and add to the second row. We will get 1i, then 0, and 0. Okay. So we have the following: x1 plus I x2 equals 0. And the vector is the coordinates of this vector should be the solutions of this equation. So one of the solutions, right? And we can take maybe, let it be 1 and I, for example, right? Okay. We can take this vector as the basis vector, right, as the eigenvector. Okay. But to form the unitary matrix, we should normalize this vector. The norm of this vector, v1, is equal to root 1 plus 1, root 2. And if we divide this vector by its length, by its norm, we will get the unit vector, and this unit vector will form the first column of our unitary matrix, right? So we should consider the vector x1. This is not a conjugation, which is equal to 1 over root 2 times 1i. So this is the first column of our unitary matrix. Next, let's consider lambda 2, which is equal to 2, and solve the matrix equation minus 1i minus I minus 1 times x1, x2 equals 0, 0. So using Gaussian elimination method, it will be 1 minus I minus 1, multiply by I and add to the second row, and we will get this 0, and then 1 minus 0. And the vector, so I will use this space, the vector v2 will be, it will be I and 1, for example. I and...
I don't understand, how did you get from that step x1 plus ix2 is equal to 0 to v1?
What this one? So it is. So I guessed just to. Or maybe okay. So if x1 is equal to 1, then we must multiply I by I to get 0, right? Okay, we can use the method of trials and efforts maybe, or to guess sometimes. Or we may solve, of course. So because x1 is equal to minus ix2, right? So from this equation, x1 is equal to minus ix2. And then we can use this vector, or instead we can take the vector, which one? So the vector, if x2 is 1, then x1 is negative I, and multiplied by this. So we can use this vector as the first column, or this one, right? It doesn't matter. Okay, and in this case, the length of this vector v2 is 1 over, or is root 2, and so to form the unit vector, we should divide by its length. Okay, and now let's find the matrix U. The unitary matrix will be 1 over root 2, and the first column will be this vector, or maybe this vector, doesn't matter. So let it be this 1 and I. And the second vector should be I1, this vector v2, I1. And this is the coefficient it is necessary to make these two vectors unitary vectors, unit vectors. This is U. And theorem states that UH times A times U. But UH is the same as U inverse, right? U inverse is the same as UH by definition of the unitary matrix, right? So it is equal to the diagonal matrix. And what is it? What are the entries of this diagonal matrix? Lambda 1 and lambda 2, so it will be 0 and 2, 0, 0, right? Okay, well, so solved. The task is solved. This task is solved. Okay, now I think it's time to finish our seminar, right? I think it's clear how to solve these tasks, and you will be able to solve them yourselves. Right? Thank you for your attention, and see you later.